Everyone is investing in AI. Almost nobody is pricing in the electricity crisis behind it. What you are seeing is not a warehouse. This is a data center, the physical backbone of the entire digital economy. Every artificial intelligence query, every cloud application, every financial transaction passes through a facility exactly like this one. Inside, the floor plan is divided into cold aisles and hot aisles. Cold air rises through raised floor tiles and enters the servers from the front. Hot exhaust air exits from the rear into contained hot aisles and is removed. This thermal discipline keeps thousands of servers running without interruption, 24 hours a day. Data center technicians install and maintain the hardware wearing electrostatic discharge wrist straps to protect sensitive components. At the core of every AI server sits the Nvidia GPU, specifically the H100 and the newer Blackwell B200. A single fully populated AI rack can cost upward of $3 million US. Between GPU servers, data moves through InfiniBand, a high-speed interconnect that allows thousands of GPUs across multiple racks to operate as a single unified compute system. This fabric is what makes large-scale AI model training physically possible. To handle the extreme heat from GPU clusters, liquid cooling is deployed. Sealed cold plates sit directly on each chip. Some facilities go further with immersion cooling. Servers fully submerged in dielectric fluid inside open tanks. No water ever contacts live electronics. Both systems are completely sealed. Outside, cooling towers reject heat through water evaporation. The white vapor rising from the towers is water, not pollution. The data center building itself produces zero direct emissions. Power infrastructure is equally critical. Large UPS battery banks ensure zero interruption during grid fluctuations. A dedicated substation steps down utility voltage directly into the facility. A single hyperscale data center can draw between 100 and 500 megawatts, equivalent to powering a mid-sized city. AI workloads fall into two categories. Training, where a model like GPT, Claude, or Gemini is built from scratch using thousands of GPUs running in parallel for weeks. And inference, where that trained model serves live user queries in real time. Training consumes far more power per job. Inference operates at massive concurrent scale. A third workload is now emerging: agentic AI. Autonomous systems that execute multi-step tasks, searching the web, writing code, calling APIs, without human input at each step. Each agentic session consumes significantly more inference compute than a single query. The network operations center monitors all of this in real time: power draw, temperature, GPU utilization, and network throughput. The hyperscalers, Amazon, Microsoft, Google, and Meta operate at global scale. A newer category of GPU cloud providers, CoreWeave, Nebius, and Lambda Labs, now supply raw compute directly to AI labs like OpenAI and Anthropic. Here's the central issue: data center power demand is projected to reach 10% of total United States electricity consumption by 2030. Utilities cannot build transmission infrastructure fast enough. Power, not chips, not land, is now the primary constraint on AI expansion. This is the defining infrastructure investment story of our decade.